Hi, my name is Quinton Yong from the University of Victoria, and today I am extremely excited to present to you our work in efficient graph summarization using weighted locality-sensitive hashing. Our approach is in the class of correction set-based summarization algorithms, where given a simple undirected graph G with nodes V and edges E, the output produced is a summary graph G bar, containing supernodes S and superedges P, along with edge correction sets C+ and C-. The goal is to minimize the size of the output representation, which is the sum of the number of superedges and correction set edges, while still being able to reconstruct G using the summary graph and correction sets. In some cases, we can allow for the reconstructed graph to not be a perfect copy of the original graph, which we would call a lossy summarization. But in this work, we'll be focusing on lossless summarization, where the reconstructed graph is identical to the input graph. The general idea of the algorithm is that we merge similarly connected nodes of the original graph into supernodes of the summary graph, so that in each single superedge, we can represent as many original edges as possible, and such that when we reconstruct the graph, we also minimize the number of corrections that we need to make. C+ are the edges that we lost during reconstruction that we need to add back in, and C- are extraneous edges induced by the superedges that we need to remove. To illustrate, this is the output representation of the previous graph, where nodes are merged into supernodes and edges are encoded into superedges and correction set edges. So now we will show how to reconstruct a graph from the output representation. So first, for each superedge connecting two supernodes A and B, we reconstruct edges between all the nodes inside A and inside B. Next, we add each edge of C+ into the reconstructed graph. And finally, we remove each edge in C- from the reconstruction. And after these steps, we have the reconstructed graph that looks like this. In this case, the reconstructed graph is identical to the original graph. So this is a lossless summarization. Next, we will describe the main steps of correction set summarization, which was originally developed by Navlaka et al. The input is the original graph G and number of iterations T. We initialize the set of supernodes so that each supernode contains exactly one vertex of V and vice versa. Next, we perform T iterations of the merging phase. So in each iteration, the set of supernodes is repeatedly updated by performing sequences of supernode merges. We choose to merge two supernodes if the number of edges in the summary representation is reduced by a significant amount due to the merge. So formally, we define the savings induced by merging supernodes A and B by the cost of merging them divided by the sum of their costs separately without merging them. The cost of a particular supernode refers to the amount that it contributes to the number of edges in the output representation. And we can calculate the cost by simulating a local encoding step where we count how many superedges and correction set edges would be created due to the edges incident to a supernode. Formally, in each iteration, we do the following. First, we select a random supernode A. Then we find the supernode B, which gives the highest savings when merged with A. If the savings is greater than a certain threshold, then we decide to merge them. And we repeat these steps until every supernode has either been selected or merged. And due to the pairwise calculation to find good merge candidates, the merging phase takes time quadratic in the number of supernodes. After T iterations of merging, we have the final supernodes of the output representation. So we can now perform the encoding phase, which encodes original edges into superedges and correction set edges. For any pair of supernodes, A and B, EAB is the set of actual edges between the nodes inside A and B. FAB is just the set of all possible edges between the nodes inside A and B. The encoding algorithm goes as follows. So for each supernode A, we iterate over each supernode B, where EAB is non-empty, or in other words, A and B have original edges between them. If the number of edges between two supernodes is less than or equal to half the number of possible edges that could exist between them, then we do not encode a superedge. Since we do not encode a superedge, in the reconstruction, we would lose all the edges between these two supernodes. So we have to add these edges into the correction set C+, so we can put them back into the reconstructed graph. Conversely, if the number of edges is greater than half the number of possible edges, then we do encode a superedge. So we add the extraneous edges induced by the superedge to C-, and then of course, we add the superedge. And once this is done, we have the output representation. And we also note that it's possible to process each pair of supernodes in parallel. The algorithm SWeG by Shin et al. Builds upon the original algorithm by Navlake et al. By adding several optimizations. So first, it introduces a dividing step, which runs in each iteration prior to the merging phase, and it divides the set of supernodes into disjoint groups. Then merges are only performed within each group instead of having to find merges in the entire set of supernodes. So supernodes are divided using supernode shingle values. For the shingle of a regular node, each node is randomly assigned the number of another node based on a random bijective function h. Then the shingle of a node is the minimum h value out of all the node's neighbors, including itself. Then a shingle of a supernode is the minimum shingle value out of all nodes inside of the supernode. Since merging is only done within each group can also be processed in parallel. SWeG also introduces superjacquard, which is an approximation for savings, since computing savings for every pair of supernodes is extremely computationally expensive. So using an approximation metric is more efficient, but it also results in slightly lower compression. The superjacquard between two supernodes A and B is defined as such, where WAV of a supernode A and a vertex V is how many nodes within A are adjacent to V. Then the sum is taken over the neighborhood of all nodes inside A and inside B. And then for each neighboring node, we compute the W value between the node and both A and B. Then we take the sum over all the minimum W values divided by the sum over all the maximum W values. So finally, SWeG has a post-processing step, which is the dropping step for lossy summarization, which drops certain edges from the output representation subject to certain quality constraints in order to further reduce the size. So despite all its optimizations, though, SWeG still has inefficiencies which hinder its performance and scalability. The dividing step changes the running time of the merge phase, which is the bottleneck step, from being quadratic in the number of supernodes to quadratic in the number of nodes within a group. However, the shingle-based dividing step creates some groups that are really large, which causes the algorithm to still run extremely slowly, both on a single-threaded machine and when parallelized in a distributed environment. Also, superjacquard, to approximate savings, results in lower compression. As for the encoding phase, the algorithm iterates over each pair of nodes A and B. So when the number of supernodes is large, this step is extremely slow on a single-threaded machine. So conceptually, we can reduce the running time of the merging phase by reducing the number of nodes in each divided group. In our work, we introduced the usage of weighted locality-sensitive hashing. Locality-sensitive hashing, or LSH, is a technique used to group similar binary sets using a hash function or hash function family, which assigns sets to buckets by some similarity metric. The more similar any two sets are, the more likely they are to be put into the same bucket. Then weighted LSH is an extension of LSH to group weighted sets instead of binary sets. In WLSH, the probability that two sets X and Y are placed into the same bucket is equal to their weighted Jacquard similarity, defined as the sum over the minimum weight of each index divided by the sum of the maximum weight of each index. So we assign each supernode a supervector of size n, where n is the number of nodes in the original graph, and each index of the vector represents a node, and the weight at each index v is WSV, which is the value that we saw before, and which is the number of nodes inside S adjacent to V. So using the formula from the last slide, we can calculate the weighted Jaccard similarity between any two supervectors VA and VB, where the weights of the vectors are just the W values. Then the sum can be taken over only the neighborhood set of the nodes inside A and B, since any node which is not in their neighborhood will simply have a W value of 0 in both VA and VB, so they won't contribute to the calculation of weighted Jaccard similarity. Notice that this is actually exactly equal to the super Jaccard between two supernodes, which is what SWeG used to approximate the savings obtained from merging. Therefore, we can use weighted locality sensitive hashing on the supervectors that we constructed and assigned to group supernodes which have high super Jaccard similarity with each other. Or in other words, have a high likelihood of reducing the size of the output representation by a significant amount when merged. So in our new dividing algorithm, we use a weighted locality sensitive hash function to generate a hash signature for each supernode. Then we divide supernodes into disjoint groups by their hash signature. The hash method that we use is densified one permutation hashing, or DOPH, which takes as input a signature length k, a random permutation h, and a binarized version of a supervector I. And it does the following. So first, the binarized supervector is just the original supervector, but replacing all non-zero weights with 1. First, we permute the vector based on the random permutation h. Next, we divide the vector into k sequential bins of equal size. Then for each bin bi with a non-zero entry, we set the hash value of bi to be the index of the first non-zero entry. Then for bins with only 0 values, we copy the hash value from the first non-zero bin to the left or right, where left or right is determined at random. So then the hash signature is just the concatenation of each of these bins hash values. So DOPH takes as input a parameter k, which determined the length of the signature. So we can modify that parameter to achieve different effects. If we increase k, then there are more possible groups to divide the supernodes into, which results in more groups, each of smaller size. If we reduce k, then we get less groups, each of larger size. So with larger k, we achieve significantly faster running time, but we also reduce the amount of compression in the output representation, since better merge candidates just have a higher chance of being placed in separate groups and not found by the algorithm. With smaller k, the groups are larger, so the merge phase is slower, but we have a better chance of finding good merge candidates, which results in better compression. Being able to tune k allows for the option of trading compression for running time, depending on which is more important for a particular application. So this diagram illustrates the effect on the number of groups, which is the red line, as well as the maximum group size, which is the blue line, on 3 data sets as we change k. We see as k increases, the number of groups increases, and the maximum group size decreases. We also introduce a method to efficiently compute the savings without the need for an approximation metric, which uses a 2-level hash table data structure that stores the information needed to compute cost and savings. However, we don't include further details about this in this talk. Lastly, we propose a more efficient and scalable encoding algorithm, which avoids the inefficient step of iterating over pairs of supernodes, which actually became a bottleneck when the number of supernodes is large in the case of very large graphs. We construct a list which contains an entry for each edge. And the entries of our form A, B, U, V, where UV is the endpoints of the edge, and A and B are the supernodes containing U, and V respectively. We can then sort this list so that between any pair of supernodes A and B, their edges are grouped together in this list. For example, we can see that in this illustration, the edges between B and C are grouped together. So we can linear scan this list, reading edges until the supernode endpoints change to get the EAB between any supernodes A and B with edges between them. So we also maintain that in each phase, our algorithm is highly parallelizable and can be run in a distributed environment to achieve better speed and scalability. In particular, the DOPH signature of each supernode can be computed in parallel. The merges between each group can be computed in parallel. And the encoding between each pair of supernodes with edges between them can be processed in parallel. So we call our approach LSH-based Divide-Merge-Encode, or LDME, and we experiment with two versions. LDME 5 is tuned for better compression with a signature length of 5, and LDME 20 is tuned for better running time performance using a signature length of 20. Compression of the output representation is formally defined as 1 minus the number of edges in the output representation over the number of original edges. And this table summarizes the data sets from the laboratory of web algorithmics that we use in our experiments. These charts compare SWeG, LDME5, and LDME20 on a single threaded machine with data sets which SWeG could complete within reasonable time of 1 day. And we show the changes over each iteration. We see that in terms of compression, LDME5, which is the orange line, achieved better or similar compression to SWeG, the red line. And LDME20, which is the blue line, had similar or slightly lower compression. In terms of total time, which is measured in seconds, LDME5 achieved 3 to 53 times speed up, and LDME20 achieved 11 to 96 times speed up. For two data sets, we show the breakdown of merge and encode times. And we see that the merge and encode times are both significantly faster, with the encode time being 7 times to 26 times faster. On large data sets, SWeG's encoding phase actually could not complete within reasonable time, while our encoding algorithm remained consistently small. These figures illustrates the final compression and total time of LDME 5 and 20 run for 60 iterations on datasets which SWeG actually could not complete within a day. We see again that LDME 5 has better compression than LDME 20, but also LDME 20 is significantly faster. The dataset Arabic 2005 has over 1 billion edges, which shows that our algorithm can actually successfully summarize billion-scale graphs using only a single machine. So here we have the results of 3 different experiments. In chart A, we have the running time of MOSO, a recent state-of-the-art in incremental graph summarization, VOG, LDME5, and LDME20 on a single-threaded machine. In this chart, we do not include VOG since it actually ran over 40 times slower than LDME on every dataset. We see that LDME5 was up to 6 times faster than MOSO, and LDME20 was up to an order of magnitude times faster. MOSO also could not complete the dataset Arabic 2005 within a day. So chart B compares the parallel implementations of SWeG and LDME in a distributed environment. And here we see that LDME achieved 3 to 24 times speed up, LDME5 did, and LDME20 achieved 3 to 36 times speed up. LDME is also shown to be more scalable in a distributed environment, as SWeG could not complete the Arabic 2005 dataset within reasonable time. Finally, chart C compares all the algorithms that we discussed using random graphs generated by the stochastic block model, and we also see that LDME achieves faster running times. So with that, we conclude our talk on efficient graph summarization using locality-sensitive hashing. Thank you very much.